Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 4th, 2026, exactly 1 week ago. It introduces a novel paradigm called drifting models that achieve state-of-the-art results with native one-step inference, reaching an FID of 1.54 on ImageNet. The paper is titled Generative Modeling via Drifting. And as we'll see later, the method offers a really compelling alternative to standard diffusion by shifting the iterative work entirely to the training phase. So Figure 1 illustrates this core concept of shifting the evolution to training time. The top row displays a sequence of contour plots where blue lines represent the target data and orange lines show the model's output. Initially on the left, the model is inaccurate, but as training progresses rightward, the orange contours drift to perfectly overlay the blue data. The graph below tracks this convergence, plotting the drifting loss on a log scale against training iterations, showing how minimizing this drift successfully aligns the two distributions. So while Figure 1 showed the global convergence, Figure 2 breaks down the mechanics for a single generated sample. Here the black dot represents a generated point X, surrounded by blue positive samples from the real data and orange negative samples from the current model. The system calculates two forces: an attraction vector, VP+, which pulls X toward the real data, and a repulsion vector, VQ-, which pushes it away from the crowded model outputs. The final drifting vector versus combines these forces, effectively guiding the sample into the high-density regions of the true distribution. So, having established those forces, Table 1 now demonstrates why balancing them is absolutely critical. The first row shows the default anti-symmetry setup, where the attraction and repulsion terms are equally weighted, achieving a solid FID of 8.46. But notice what happens in the lower rows when we disrupt this balance. Scaling either force up by just 50% causes the performance to collapse, with error rates skyrocketing, which confirms that precise equilibrium is necessary for the model to learn effectively. Figure 4 visualizes the actual training evolution on two separate 2D toy datasets. The top series targets a complex grid pattern, while the bottom series aims for a spiral. In both examples, the orange-generated samples begin as a tight, undefined cluster at iteration 0. Over 2,000 training steps, they expand and precisely align with the blue ground truth shown on the far right. The line charts underneath track the loss, which steadily decreases, confirming that minimizing the drift effectively pushes the generator toward the correct distribution. Alright, while the toy examples confirmed the theory, applying this to real images requires a robust feature space to calculate those drift vectors. Table 3 compares different self-supervised encoders for this task. The top rows show that standard methods like SimCLR and MoCoV2 achieve FID scores around 8 to 11. However, the middle section introduces a customized latent, masked autoencoder. We see that simply increasing the network width from 256 to 640 steadily improves performance. Finally, the bottom rows show that extending the training to 1280 epochs with classification fine-tuning drives the FID down to 3.36. Okay, after optimizing those feature encoders, Table 5 presents the final system-level comparison on ImageNet 256. The table divides existing methods into multi-step models, which are slow but accurate, and single-step ones, which often struggle with quality. Crucially, the bottom section highlights the drifting model. With the large L2 variant, it reaches an FID of 1.54 using only one inference step. This result not only sets a new record for single-step generation, but also rivals the performance of computationally expensive multi-step baselines like SIT-XL. Well, while the previous table focused on latent space, Table 6 shifts the comparison to direct pixel space generation. The top rows list multi-step diffusion models and single-step GANs for context. The bottom section highlights the drifting models. Specifically, the L16 variant achieves an FID of 1.61 with just one inference step. This result beats strong baselines like Style, G, A, and XL at 2.30 and effectively matches the quality of computationally expensive models like Pixel DIT. So wrapping up, this work fundamentally challenges the idea that high-quality generation requires slow, iterative steps. By moving the distribution evolution to the training phase, drifting models achieve state-of-the-art results with just a single inference step. This opens a promising new direction that bypasses the complexity of diffusion solvers entirely. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.